Okay, so let's look at a couple examples of how we would apply the polar coordinates in our double integrals. So the first thing I want to look at is let's evaluate the double integral over s of x plus 2y dA using polar coordinates. I have to tell you what s is. So S is going to be the following region. So it's the sector here where this is the point 2, well, let's comma 0 in rectangular. And this is the point square root of 2, comma square root of 2 in rectangular. Okay, so we're looking at this sector. And you can see that this is a little bit of a mess to try to deal with in rectangular coordinates. So this is why we want to use polar coordinates. This arc here, let me use this arc here has r value 2. So I'm just going to tell you that the arc has the equation r equals 2. And down here, we're at r equals 0. So if I were to describe this region using, polar coordinates, well, my r value is how far out I'm going out from the origin. I'm going to start at 0, and depending on what point I'm at, I'm anywhere between 0 and 2. So my bounds on r are 0 to 2. Now what about theta? Well, again, think about as you're moving along this way, what your theta might be. So if this were my point, I would draw an angle here, and this is theta, right? So when I'm down here, what is theta? Well, I'm along the x-axis, so theta is 0. And now what am I up here? Well, do you remember what points look like along a circle of radius r? These are of the form r cosine theta, r sine theta, where here we know we're along this circle, so r is 2. So 2 cosine theta, 2 sine theta, and it equals root 2 comma root 2. So what's the angle that has a cosine of root 2 over 2 and a sine of root 2 over 2? It's pi over 4. Now, if you don't remember that, of course, you can use the inverse cosine function on your calculator to spit it out. But that's one of those special angles you should know. All right, so I've got my description of this region in polar coordinates, and now I just apply the result from the last video. So my double integral over r, in this case we've got an s, can be rewritten as the integral from theta equals 0 to pi over 4 of the integral from, in this case, the bounds on r don't involve theta, from 0 to 2 of r cosine theta, that was x, right, plus 2y, so plus 2 r sine theta, r dr d theta. Okay, so to integrate this, I'm going to want to collect my r's together. So I've got the integral from 0 to pi fourths. I could pull an r out of each term here in my sum, and I've got this r here. So that's going to give me an r squared times the quantity cosine theta plus 2 sine theta dr d theta. Oops, I lost my bounds on r, sorry. Integral from 0 to 2. All right, now we can integrate. So I'm going to let you handle this one. The only thing new from here is that now my variables are r and theta instead of x and y. So you've been practicing with these double integrals for a while now, and so hopefully you can integrate this without too much trouble. Let me tell you what you should get, and if you aren't able to get that answer, you should set up a Zoom meeting with me so we can walk through it together. All right, so dot, dot, dot. What you should get is 16 minus 4 root 2 divided by 3. Okay, let's try another example. I want to find the volume V of the solid bounded by the xy plane and the paraboloid z equals 25 minus x squared minus y squared. Okay, so roughly you should let yourself get a rough sketch of what's happening here. I'm not going to be too careful, but I've got a paraboloid and it hits the xy plane in a circle, and I'm looking for the volume of this solid. All right, so there's a rough sketch of what's happening. My region of integration is down here in the xy plane. It's this circle. That's a terrible drawn circle, but you know what I mean. It's the circle that we get down here in the xy plane. And so we need to figure out what that circle is. Well, it's the circle we get when z equals 0, right? So 25 equals x squared plus y squared. Okay, so my region of integration here is a circle of radius 5. Oh boy. Okay. So, let's put my 5 and my 5 there. Now, we could have done this in the last section and just integrated using rectangular coordinates, but you'll see here that polar coordinates are a lot easier to handle. And in fact, we can lessen our work a little bit because since this, and this is only because z itself is symmetric about the x-axis, about the z-axis. So z, I mean the paraboloid. Finding the volume above the region R is equivalent to finding the volume above the region here and then just multiplying by 4. Okay, so that's what we're going to do. Now that only works in this problem because my surface over here on the left is the same over all 4 of these regions. Okay. All right, so here's my region R in blue. Let's find the bounds of R using polar coordinates, and then we'll think about what it would look like using rectangular coordinates. All right, what I would like you to do is actually just pause the video and try it yourself before you see my answer. So I'll give you a second to pause while I take a drink, and then you can check my answer. All right, so here's 0 and here's pi halves. So theta here is going to run from 0 to pi halves. And what about r? Well, on the circle of radius r goes from 0 here to 5 on the outside of the circle. All right, what if I wanted to use rectangular coordinates to describe this? Well, this is the top half of the circle of radius 5. So this has the equation y equals the square root of 25 minus x squared. It's the positive square root because we're on top. And so let's think about taking a vertically simple region. So here's delta x. Okay, so my y values go from 0 down here up to the circle. So y, whoops, it's bounded by 0 up to the square root of 25 minus x squared. And x, well, think about what happens as these sections move horizontally. X goes from 0 over here to 5. Okay, you can see that the bounds here on the polar regions are just a little bit nicer, right? I don't have any functions of other variables. All right, so let's set up the integral using polar coordinates. Okay, so the volume is going to be 4 times the integral from theta equals 0 to pi over 2 of the integral from r equals 0 to 5 of my function, so z was 25, minus x squared, which in polar coordinates is r cosine theta squared, minus r sine theta squared, and then r dr d theta. Okay, now I want to be real careful that I make sure that r gets distributed, so I'm going to put that in parentheses here. Okay, again from here, this is just a basic double integral, and so I'm going to let you try to solve so that this video isn't too long and my voice isn't boring you too much. All right, what you should get is 25 times 25 divided by 2 times pi. If you aren't able to get that, please let me know and we can talk about it.